this is the lecture number 25 of our course on fundamentals of transport processes. We were discussing potential flows, high Reynolds number flows, inviscid and irrotational. So, if you recall, we first discussed some integral theorems for vector calculus, so that we could derive the conservation equations without reference to an underlying coordinate system. And then we derived the Navier-Stokes equations, incompressible Navier-Stokes equations for the mass conservation and momentum conservation. So, one scalar equation for the mass conservation plus 3 vector equations for momentum conservation. There are 4 variables, there are 3 components of the velocity and the pressure, and we looked at various boundary conditions that have to be specified for these equations. We then scaled the momentum conservation equation, got the dimensionless Reynolds number, ratio of inertia and viscosity, and then we looked at simplified cases in the limits of low and high Reynolds numbers. We had completed our discussion of the viscous Stokes flow solutions, and then we had started discussion of the high Reynolds number potential flow solutions. So, this is high Reynolds number, potential flow. 2 requirements for potential flow, one is inviscid and the other is irrotational. Irrotational implies that the vorticity, which is del cross u, is equal to 0 everywhere within the fluid, and inviscid means you are setting the viscosity equal to 0. So, the original Navier-Stokes equations were del dot u is equal to 0 and rho into partial u by partial t plus u dot grad u is equal to minus grad p plus mu del square u. Okay. Potential flow, this term is being set equal to 0, and we could use the irrotationality condition to simplify this term here. Since the flow is irrotational, del cross u is equal to 0, I can always express the velocity as the gradient of a potential. I can always express the velocity as the gradient of a potential. Okay. Then the mass conservation equation now just becomes Laplacian of the potential equal to 0, because I get del dot grad phi is equal to 0. The divergence of the gradient of phi is equal to 0, or del square of the potential is equal to 0. And if you recall, we could simplify this term in the momentum conservation equation from the condition that the flow is irrotational. And once I do that, I get an equation of the form the gradient of, should have plus a body force here, okay, P plus rho partial phi by partial t plus half rho u j square plus any potential is equal to a constant, is equal to 0. The gradient of this entire function is equal to 0. That means that this function is equal to a constant. Okay. The gradient of this entire function is equal to 0. It means that this function is equal to a constant. So, P plus rho d phi by dt plus is equal to this constant. Note that originally my equation was a vector equation. Okay. This equation is actually a vector equation, okay, where I have used here the fact that f vector is equal to minus the gradient of a potential. Okay. In this simplification, I have used the fact that f is conservative, and therefore, it can be expressed as minus of the gradient of a potential. So, coming back to my earlier point, momentum conservation equation originally was a vector equation. I reduced it to an equation which was basically the gradient of a scalar function is equal to 0. Gradient is a vector. However, since the gradient is equal to 0, that means that this function is equal to a constant. So, from this vector equation I have reduced it to just one equation here. The original momentum conservation equation had 3 equations for each for 3 components of the velocity, whereas my reduced equation is just a scalar equation. I have 2 scalar equations, Laplacian of potential is equal to 0 and this equation for the pressure, solved for 2 scalars, the potential and the pressure. The velocity of course is given by the gradient of the potential. So, this is the simplification in the potential flow case. The stress tensor for the potential flow is just given by minus p times the identity tensor. Okay, so, the stress tensor is just equal to minus p times the identity tensor. There is no viscous part. And as I had mentioned in the last lecture, because there is no viscous part, one cannot satisfy the tangential velocity or tangential stress boundary conditions at the surface. The tangential velocity boundary condition, that is, in order for the flow to come to a stop at the surface, okay, at a stationary surface, you require momentum diffusion from the surface. In our potential flow approximation, we've set the viscous term equal to 0. There is no momentum diffusion. Therefore, the velocity field does not decrease to 0 at the surface. Therefore, you have to solve these 2 equations subject to the normal velocity boundary condition and the normal stress boundary condition. As I had explained in the last lecture, the potential is still linear in the velocity, because I have expressed u is equal to grad phi. The pressure, however, is no longer linear in the velocity, because it is proportional to half u square. Okay. You have a term that goes as half u square. So, because of that, the pressure is no longer linear in the velocity. It is a nonlinear function of the velocity. Just to go back and make a reference to our previous course, we had looked at transport of mostly heat and mass. In that case, we had divided the regimes into 2 types. Okay. So, the heat or mass conservation equation in that case would be of the form partial c by partial t plus u dot grad c is equal to d del square c. Okay, so, that would be the form of the mass conservation equation. C is a scalar. Okay, is equal to d del square c. And there we had divided into 2 different limits. One is the diffusion dominated regime, where we just solve d del square c is equal to 0. Okay. One could also have a convection dominated regime in the high Peclet number limit. In the low Peclet number limit, of course, you just solve del square c is equal to 0. In the high Peclet number limit, there is a convection dominated regime in which you solve this equation partial c by partial t plus u dot grad c is equal to 0. And if the flow was steady, the equation would just reduce to u dot grad c is equal to 0. The solution of this equation is basically that there is no variation in the concentration along the streamlines. So, if I am going along the streamlines, the concentration is remaining a constant along that streamline. Okay. So, in that case, the solution in that case was trivial. Okay. The u dot grad c is equal to 0 basically says that if I go along a velocity streamline, there is no variation in concentration along that streamline. So, in that case, there was really no problem to solve. Once I knew what the velocity field was, I know exactly what the concentration is everywhere, just from the condition that there is no variation in velocity along the streamline. In this case, of course, there is a more it's a more complicated system. The reason is because I have this additional fluid pressure here. Okay. In the case of mass and heat transfer, there is no equivalent of the fluid pressure, which tends to maintain a constant density throughout the flow. In the case of fluid mechanics, there is a fluid pressure which maintains a constant density throughout the flow. Therefore, I get a non-trivial result for the relationship between the pressure and the velocity. So, we are solving the same convection dominated regime, except that we have this additional fluid pressure here, and that makes all the difference. Okay. That is why you have this potential flow regime in fluid mechanics. You do not have equivalent problems in heat and mass transfer. It is because of the fluid pressure. For this potential flow solution, you can show exactly various things. Okay. The simplest thing to show is that there is a non-zero fluid velocity within the fluid only if there is a non-zero normal velocity at the boundaries of the flow. Okay. Alternatively, one can show that if there is no normal at boundaries, the fluid velocity is 0 everywhere. I should emphasize that there is no normal velocity at the boundaries. So, if at all bounding surfaces the normal velocity is identically equal to 0, then the fluid velocity everywhere within the fluid has to be equal to 0. This is in contrast to, for example, the case of viscous flows, where, for example, in the flow through a channel, for example, you could have a velocity that is non-zero. Okay. I am sorry, this is you could have a velocity that is non-zero, even though the normal velocity at the surface is equal to 0. In this particular case, the bottom plate is stationary, the top plate is moving with a velocity u, but that velocity u is tangential to the surface, it is not normal. So, there is no normal velocity of any of the surfaces, but despite that there is a fluid velocity in the fluid. The reason is because there can be diffusion of momentum perpendicular to the flow direction, and that causes the fluid to flow. In the case of a potential flow, we are neglecting this momentum diffusion, and because of that, unless there is a normal velocity, there cannot be any fluid flow. This is an exact result, and I will briefly show you how that comes about. The total kinetic energy is the integral over the entire volume of the kinetic energy per unit volume. The kinetic energy is mass times the velocity square. The local kinetic energy per unit volume is mass per volume density times the velocity square. Okay. Is equal to half rho ui square. This is always a positive quantity. Okay. It is positive semi-definite. It is always greater than or equal to 0, because the density is positive and u square is a positive number. Since the density is a constant, I can write this as half rho integral dV times ui square. Okay, this is equal to half rho integral dV ui into ui. Okay, ui times ui is ui square. For one of those ui's, I express the velocity in terms of the gradient of the potential. Okay. So, I will write it as half rho integral dV ui times partial phi by partial xi. Okay. Integrate this by parts. Okay. Integrate this by parts, I will get half rho integral dV partial by partial xi of ui phi minus phi partial ui by partial xi. Integration by parts. we know that the divergence of the velocity, the second term on the right hand side, has to be equal to 0 from the incompressibility condition. Okay. The second term on the right hand side is the divergence of the velocity. So, this has to be equal to 0 just by incompressibility. Okay. So, this is equal to half rho integral over the volume of partial by partial x I of u I phi. So, this is the divergence of u times potential integrated over the entire volume. It can be reduced to a surface integral of the unit normal times the vector. So, the integral of a divergence of a vector over the volume is equal to the integral of the unit normal times the vector over all the surfaces that are bounding this volume. Okay. Integral over the surfaces of n I u I phi. So, this is a surface integral of u dot n, the velocity dotted with the unit normal to the surface, times the potential. So, clearly if u dot n is equal to 0, this integral is equal to 0. Okay. This integral is equal to 0 if u dot n is equal to 0. That is, there is no normal velocity to the surface at any point, then this integral is equal to 0 and u dot n is equal to 0. If u dot n is equal to 0, the kinetic energy is equal to 0, okay, because we said the kinetic energy is half rho integral of u dot n times potential. And if the kinetic energy is 0, you can see from here, if the kinetic energy is equal to 0, the velocity has to be 0 at each point within the flow. Because if somewhere the velocity is non-zero, whether it is positive or negative, the kinetic energy will always be positive, because it's proportional to the square of the velocity. Therefore, this says that unless if u dot n is equal to 0 on all bounding surfaces, the total kinetic energy is 0, and therefore, the velocity is 0 everywhere within the flow. That is, one has to have a non-zero normal velocity at the surfaces that are bounding the flow in order to have in order for the fluid to be moving. If the normal velocity is 0 at each and every point within the flow, that means that the velocity within the fluid is also 0 everywhere. The system is stationary. This normal velocity at bounding surfaces can be of various kinds. Okay. You could have, in the case of external flows, okay, for example, you could have a system where the velocity on the walls is equal to 0, but there is some object that is moving with a constant velocity u. That means that the normal velocity on this surface is non-zero. One could also have flows where there is an inlet of fluid. Okay. For example, the normal velocity at these surfaces, the top and bottom surface, is equal to 0. However, one could have velocity coming in at an open surface. Okay. You could have velocity coming in at an open surface. So, either you have to have an object moving within the fluid such that the velocity perpendicular to the surface is non-zero, or you have to have some external source of fluid coming in, okay, at an open surface. Only in that case will you have a non-zero velocity acting on the within the fluid. If there is no normal velocity everywhere, surfaces may be moving tangential. Okay. So, you could in general have a tangential velocity at a surface like this. That will not cause a flow within the fluid in potential flow, because we have neglected momentum diffusion. One could derive other relationships. When we looked at viscous flows, I said the equations are linear, and because the equations are linear, the solutions are unique. The solutions exist and they are unique. That was because the Stokes flows are linear. The velocity, the pressure is linear in the velocity, the stresses are both linear in the velocity. In this case, the pressure is a nonlinear function of the velocity, but still it is possible to show that the solution is unique for potential flow. So, we will briefly look at the uniqueness of the solution. Uniqueness implies that for a given set of normal velocities at the boundaries, there is only one potential flow solution. Okay. For, let me call this as for specified at boundaries. Let me just say potential flow solution is unique. The potential flow solution is unique for a given specified normal velocity boundary conditions at all boundaries. Okay. So, in order to prove this, we will first postulate the opposite. Okay. We will first assume there are two solutions. Satisfy, assume there are two solutions, we call that as the normal velocity conditions. At the surface. So, we will first postulate that there are two possible solutions, both of which satisfy this normal velocity condition, and then we will show that both of these solutions turn out to be identical to each other. Okay. So, if you look at the integral of the volume of ui star minus ui into ui star minus ui. Okay. This is the integral of a square of some number integrated over the volume. Okay. This always has to be greater than or equal to 0. There are two potential flow solutions, both of which are satisfying the same boundary conditions. If I take the integral over the volume of ui star minus ui the whole square, okay, this integral has to be greater than or equal to 0. If this integral is equal to 0, that means that ui star is equal to ui everywhere, okay, because the square of a number is equal to 0. That means that number, the integral of a square of some function is equal to 0, means that that function is equal to 0 everywhere. Both of these are potential flow solutions. So, therefore, I can write this as integral dv, okay, times, for the second velocity I will write it as the gradient of a potential. Okay, for the second velocity, okay, the second ui star minus ui, I will write it as the gradient of a potential. I will write it as the gradient of a potential. Once again, integrate by parts. Okay. Once again, integrate by parts. The second integral, I have the divergence of ui star minus ui. Both of these velocities satisfy the potential flow condition. Mass conservation requires that the divergence of both of these is equal to 0. So, this one goes to 0, and therefore, I get this is equal to integral dV of partial by partial xi of ui star minus ui. The divergence of a vector integrated over a volume is equal to the unit normal times that vector integrated over the surface. Unit normal times that vector integrated over the surface. Okay. So, this is what is equal to the original function that I had I, okay, is equal to this one. We had postulated two different velocity profiles ui star and ui, both of which satisfy the same normal velocity condition at the surface, both of which satisfy the same normal velocity boundary condition at the surface. This has shown you that this integral ui star minus ui the whole square integrated over the volume has got to be equal to the unit normal times ui star minus ui. That is equal to 0, simply because both velocities satisfy the same normal velocity boundary condition. Therefore, n dot u star is equal to n dot u. Therefore, this is equal to 0. Okay. Therefore, I get the condition that I is equal to 0, okay, provided both velocity profiles satisfy the potential flow condition. However, if this integral is equal to 0, it implies that u star is equal to u everywhere within the flow. That means that the potential flow solution is unique. Okay. So, for a given set of boundary conditions, normal velocity boundary conditions, one can show that the potential flow solution is always unique. One can also show what is called the minimum kinetic energy principle. Okay. What the minimum kinetic energy principle states is as follows. Okay. For a given set of conditions at surfaces, the kinetic energy, the total kinetic energy of a potential flow is smaller than that of any other flow. So, let us say that we have two solutions for the velocity u and u star. Okay. We have two solutions for the velocity, out of which the velocity u can be written as the gradient of a potential, u star not necessarily so. It could be any solution. It could be a solution which has some rotation in it, for example. Okay. U star is not necessarily a solution of the potential flow equations. However, it has to satisfy the incompressibility condition. Okay. So, therefore, I require that del dot u star is equal to del dot u is equal to 0. Both velocity profiles satisfy the incompressibility condition, but the velocity u in addition satisfies the potential flow equations. For this, one can show that the kinetic energy, okay, which is integral dV of half rho u square for the potential flow, is always smaller than the kinetic energy for the general flow. Okay. That is the minimum kinetic energy principle. That is the kinetic energy for a potential flow is always smaller than the kinetic energy for a general velocity profile. So, in order to prove this, what we do is we take the difference between the two, kinetic energy for the general velocity profile minus that for the potential flow is equal to half rho integral dV of ui star square minus ui square. So, I have to prove that this is always a positive number. Can simplify this as half rho integral dV of two terms ui star minus ui the whole square, okay, plus 2 ui into ui star minus ui. If you just expand out this term ui star minus 2 ui star plus ui square plus add the second term 2 ui star minus 2 ui square, I will get back this original equation. Okay, so far so good. Okay. So, this first term here is always positive. This first term here is always positive. What about the second term? Okay, what about the second term? Okay. So, I will write this as half rho integral dV ui star minus ui the whole square plus rho integral dV ui into ui star minus ui. And in the second expression, we know that ui can be written as the gradient of a potential. Okay. The velocity u can be written as the gradient of a potential. Okay. Rho integral dV of ui is the solution of the potential flow equation. So, I can write ui as the gradient of a potential. Minus ui, and by now it will be familiar what we are about to do. Okay, we are going to integrate this by parts. Okay. So, this will be equal to half rho integral dV plus rho we are going to integrate this out by parts. Okay. In the second integral on the right, the second term contains the divergence of ui star minus ui. However, we have postulated that both ui star and ui are both satisfy the mass conservation equation. Therefore, the divergence of the velocity turns out to be equal to 0. Okay. I am just left with half rho integral dV of ui star minus ui the whole square plus rho and integral of the over the volume of the divergence of some vector is equal to integral over the surface of the unit normal times that vector. Therefore, I get half rho plus n dot u star minus u times the potential. However, we had said that both the velocities, the potential flow solution u as well as the other solution which does not satisfy the potential flow condition u star, both of them satisfy the same normal velocity boundary condition at all surfaces. Okay. Both the velocities u star and u satisfy the same normal velocity boundary condition at both surfaces. Therefore, this difference has to be equal to 0. N dot u star minus u at the surfaces, this should be a surface integral, the integral at the surfaces has to be equal to 0. That means that the difference K E star minus K E has to be a positive number. The difference in kinetic energy between the flow which did not necessarily satisfy the potential flow conditions and the flow that did satisfy the potential flow conditions, that difference has to be positive. That means that the potential flow solution has the lowest kinetic energy, okay, of any solution that satisfies the incompressibility condition as well as the normal velocity condition at all boundaries. So, this basically tells us that the kinetic energy of a potential flow has to be a minimum. Note that the kinetic energy for the flow can be expressed purely in terms of the surface integrals themselves. Okay. As I showed you previously, kinetic energy of the flow is equal to half rho integral over the volume of u I square is equal to half rho integral over the surface of n I phi times u I, n dot u times the potential. That means that in order to find out the kinetic energy of a potential flow, one does not need to know what the velocity is everywhere within the fluid. It is sufficient to know what is the potential only at the bounding surfaces, the potential plus the velocity. The velocity of course is the gradient of the potential. So long as you know the potential and its gradient at the bounding surfaces, you know exactly what the kinetic energy is for the entire flow. So that is one advantage of dealing with potential flows. So next let us solve the simplest problem, the simplest potential flow problem, that is the flow around a sphere. Potential flow solution for the flow around a sphere. I have a sphere that is moving with some velocity u vector, and I want to know what is the velocity field around the sphere. So, I have to solve for the velocity potential del square phi is equal to 0. Okay. The Laplacian of the velocity potential is equal to 0 with the normal velocity boundary conditions, that is u I n I is equal to capital U I. Note that we cannot satisfy the tangential velocity boundary conditions in this particular case, because we have neglected the viscous stresses, and therefore, it is not possible to satisfy the tangential velocity boundary conditions. We can satisfy only the normal velocity boundary conditions. So, to solve del square phi is equal to 0 with this boundary condition. Okay. So, this boundary condition basically says that the unit normal times the gradient of the potential is equal to some fixed value. Clearly, the potential is a linear function of capital U. Okay. It is a linear function of capital U, because when I take its gradient and dot it with the unit normal, that has to be equal to capital U dot n. Okay. N itself is a unit normal on the surface. Okay. So, if the potential is linear function of capital U and it satisfies Laplace equations, the velocity on the surface of the sphere is equal to u dot n. Of course, since the sphere is in an infinite medium, the velocity far away has to go to be 0. Okay. So, the velocity far away has to be equal to 0. The velocity at the surface of the sphere itself satisfies the normal velocity boundary condition. That means that the potential is a linear function of the velocity of the sphere itself. Okay. Whichever axis the velocity of the sphere is, the potential will be in general a linear function of this axis. Okay. We know the solutions for the Laplace equations, growing harmonics and decaying harmonics. In this particular case, we cannot have growing harmonics because the velocity has to go to 0 far away. The only solutions are the decaying solutions for the velocity profile. Now, for the decaying solutions, I require that phi has to be some linear combination of these fundamental solution, the first harmonic, and so on. Okay. So, you get all these multiple solutions, The first one is a scalar, the next one is a vector, third one is a second order tensor, and so on. It has to be some linear combination of these harmonics. It has to be linear in one of these harmonics, or a sum of linear functions of these harmonics, and it has to be linear in the sphere velocity, because I said because of the no normal velocity boundary conditions, okay, the normal velocity boundary conditions require that the potential has to be linear in the velocity capital U. The potential is a scalar. So, there is only one way that you can get a solution which is linear in the vector u and in one of the spherical harmonics. Okay, there is only one way that you can get a solution that is linear in capital U and in one of the spherical harmonics, and that is just some constant into uj times the vector. This is the only combination which will be linear in the velocity u as well as linear in one of the spherical harmonics, and it will be a scalar solution. So, this is the only possible solution, okay, for the potential function. Of course, this satisfies Laplace equation. There is an undetermined constant here a, which has to be determined from the boundary conditions u dot n is equal to capital U dot n. Okay. So, this solution is going to be equal to a u j x j by r cubed. The velocity is equal to partial phi by partial xi. Okay. So, we know how to take the gradients of this fundamental solution and the higher harmonics. Okay. So, that is the solution for the velocity, okay, where a is the undetermined constant. Okay. The boundary conditions state that u I n I is equal to capital U I times n I. On the surface of the sphere, since I fixed my origin at the center of the sphere, okay, I fixed my origin at the center of the sphere. On the surface of the sphere, the unit normal on the surface of the sphere, the unit normal is in the same direction as the position vector. Okay. I fix my origin at the center of the sphere. Therefore, on the surface of the sphere, the unit normal is in the same direction as the position vector. That means that the unit normal is equal to the position vector divided by its magnitude. Is equal to the position vector divided by its magnitude. So, that is n I. Okay. So, therefore, I have a u j into delta I j by r cubed minus 3 x I x j by r power 5 times x I by r is equal to u I x I by r. Okay. This is on the surface of the sphere at the location at r is equal to the radius of the sphere. Okay. So, let us put at r is equal to r here, where capital R is the radius of the sphere. Okay. I can multiply these. Okay. A u j times delta I j gives me u I. So, I get a u I x I by r cubed minus 3 a u j x I square x j by r power 5 is equal to u I x I by r. X I square, which is x 1 square plus x 2 square plus x 3 square, is equal to r square. Okay. And u j x j is u dot x, u I x I is also u dot x. So, these are all the same things. Okay. So, I will get minus 2 u j x j by r cubed is equal to u I x I by r, there is an a here, I am sorry, there is an r power 4. And r power 6. I should note that I am multiplying throughout by this xi by r. Okay. Xi by r here. So, when I get 1 over r cube times xi by r, I get 1 over r power 6. Okay. So, this. Okay, so, this gives me the value of A. Okay. Therefore, if this is true at r is equal to capital R, that means that A is equal to minus r cube by 2. Okay. So, that gives me the constant. The 0 nominal velocity boundary condition gives me the constant A in the expression for the potential here. Okay. So, my final expression for the potential becomes phi is equal to minus r cubed by 2 u j x j by r cubed. Okay. So, there is a potential, and the velocity u I is equal to minus r cubed by 2 into delta I j by r cubed minus 3 x I x j by r power 5. Okay. So, those are the potential and the velocity fields. Okay. This can be written quite easily in a coordinate system, in the r theta coordinate system. If I take u as the axis, okay, this is r and this angle is theta. U j times x j is just u r cos theta, okay, because u dot x is equal to u times r times the cos of the angle between the two. So, this just becomes equal to minus r cubed by 2 u cos theta by r square. Okay. And from this I can get the derivatives, the velocities in the r and theta directions. Okay. U r is equal to partial phi by partial r, which will be equal to minus r cubed u cos theta by r cubed. Okay. And u theta is equal to 1 by r partial phi by partial theta is equal to by 2 r cube. So, these are the two components of the velocity profile, u r and u theta for this particular case. Next, we can evaluate the kinetic energy of the fluid, okay, the fluid that is moving around the sphere. The first question that we usually address is the drag force that requires the calculation of the pressure around the surface of the sphere. Okay. So, we will do that in the next lecture, but before we do that I will just briefly here calculate the potential energy. Okay. The potential energy is equal to, as I said, in this particular case this will be integral dV half rho integral over the surface of if you recall, I just derived for you that the potential energy can be reduced to just an integral over the surface, half rho integral over the surface ds of phi n j u j. Okay. So, in this n is basically the outward unit normal to the fluid, okay, the outward unit normal to the fluid. Okay, this n is the outward unit normal to the fluid in our derivation, because we integrate over the fluid volume. Integral of the divergence of a vector over that fluid volume is equal to the integral of the unit normal times u, the outward unit normal over the surface. In this particular case, I have a sphere that is moving with some velocity u. The outward unit normal to the fluid actually acts into the sphere. The outward unit normal to the fluid is actually acting into the sphere. Okay. Therefore, this is equal to minus x j by r on the surface. Okay. Minus half rho integral ds phi u j into x j by r. However, we know that small u dot n on the surface is equal to capital U dot n on the surface, because I have u I n I is equal to capital U I n I on the surface. Okay. So, I can also write this as minus half rho integral d s phi u j x j by r. Okay. And for this phi, I substitute phi is equal to minus r cubed by 2 u j x j by I should use another index here by r cubed. Okay. Therefore, the kinetic energy becomes r cubed by 4 times rho integral ds of u I x I by r cubed into u j x j by r. This is integrated over the surface at r is equal to capital R. Okay. This integral is over the surface at r is equal to capital R. Okay. And I can set r is equal to capital R here to get rho by 4 capital R integral over the surface. Yes. Okay. And once I calculate this integral, we have already calculated this integral over the surface of x I x j is equal to a delta I j, multiply both sides by delta I j, and I will get a is equal to 4 r power 4 by 3. Okay. 4 r power 4 by 3 is what you get for a. Okay. So, this is equal to 4 r power 4 by 3 delta I j. With this, the kinetic energy becomes rho into rho by 3 r cubed. This becomes 4 pi pi r cubed square. Okay. Is equal to half rho u j square into 2 by 3 pi r cubed. Okay. Half rho u square into 2 by 3 pi r cubed. Okay. Rho into 2 by 3 pi r cubed. Okay. Rho is the fluid density. 2 by 3 pi r cubed is half the volume of the sphere, because 4 by 3 pi r cubed is the volume of the sphere. Okay. So, rho into 2 by 3 pi r cubed is 1/2 of the volume displaced by the sphere. Okay. 2 by 3 pi r cubed is 1/2 the volume of the sphere. That multiplied by the fluid density rho gives me 1/2 of the mass of the fluid displaced by the sphere. Okay. So, therefore, this kinetic energy I can write it as 1/2 m a times u square. Okay. m a is what is called the added mass. Note that this kinetic energy is the kinetic energy of the fluid that is flowing around the sphere, not the kinetic energy of the sphere itself. Kinetic energy of the sphere itself will be equal to half times the mass of the sphere times velocity square. In addition, because the particle is moving fluid around it, there is going to be an additional kinetic energy for the fluid flow around that sphere. That kinetic energy is equal to half m a times u j square, where this m a is equal to the added mass. This added mass is rho times 2 by 3 pi r cubed. Okay. Rho into 2 by 3 pi r cubed is 1/2 of the mass of fluid displaced by the sphere, 1/2 density of fluid times the volume of the sphere. Therefore, this added mass is equal to 1/2 of mass of fluid displaced by the sphere. So, that is the added mass, it is 1/2 of the mass of fluid displaced by the sphere. So, in addition to the kinetic energy of the sphere itself, there is an additional kinetic energy because there is fluid that is moving around the sphere. Kinetic energy of that fluid moving around the sphere has to be proportional to the density of the fluid, of course. The total kinetic energy is equal to half the velocity of the sphere square times 1/2 of the mass of fluid displaced by the sphere, or the added mass. So, for this particular sphere moving in a fluid, we got the exact result that the added mass is equal to 1/2 of the mass of fluid displaced by the sphere. If you had some other more complicated shape of an object moving through a fluid, then the added mass would not be 1/2, it would be some other fraction. But since in potential flow one can always reduce the kinetic energy to a surface integral, one can always find that the added mass is proportional to the density of the fluid times some fraction or some number times the mass of fluid displaced by the sphere. So, this relation just comes out of the fact that I have an exact result for the potential and the kinetic energy is just related to a surface integral. Okay. In the case of other more complicated shapes, see in this case I got uj xj by r cubed as a solution. Potential decreases 1 over r square because it is proportional to uj times xj by r cubed. Therefore, the velocity goes as 1 over r cubed. The solution for the potential is a dipole solution, it goes as 1 over r square. Okay. If I had a more complicated shape, I would have other higher order terms, but the leading order term would still be the 1 over r square term, in contrast to viscous flow where we had a solution proportional to 1 over r. And because of this, I get a solution for the kinetic energy as an integral over the surface, and from that I have evaluated the added mass. Next lecture we will continue this. We will look at the pressure, the force exerted, the pressure on the surface and the net force exerted by the sphere on the fluid, both under steady motion as well as when it is accelerating. As you expect, for an accelerating sphere, the force will be equal to the added mass times the acceleration of the sphere, just as kinetic energy is equal to half added mass times the velocity square. We will continue this in the next lecture. We will see you then.